All right, so we're going to try putting together a couple of examples. We'll go through these again in class, but figured I'd make a video of them now so that if you want to reference this or go through it before we get there, you got something to work with. We're going to be doing two examples from the book. One using node voltages, one using mesh currents. These would be pretty much the examples that we tried to do on Tuesday, but weren't getting very far with. So I'm going to try to go through them again, try to be more specific and kind of step by step, and I think we can get something good. Just grab a marker here. So first guy, this is going to be from, let's see, page 125. In the book, it's example 4.3-3, in case you want to look at it later on. So this is going to be us trying to set up some node voltage equations and try to work through the problem. So in this problem, given a circuit, something like this. Voltage source up top, a couple resistors in the middle, current source there. There's another voltage source. We have one more current source over here. Went that way. All right, let's label some stuff. I'm just labeling the nodes A, B, and C. This one's not filled in. These are filled in just because I forgot to draw the circles. So those are all nodes. If you look at the example, it has a ground drawn in. I'm not drawing that in right now, just so I can explain a couple things first. So we've got a voltage source up here, voltage source down here, current source, a couple of resistors. We are interested in the voltage at C. Now, when you say voltage at C, what is that? Because voltage is always measured between two things. It's the difference in electrical potential energy between 2 points. So when I say, what's the voltage at C, or I ask that, I have to say what the other point is. We can ask it across a resistor. Maybe we can, if we specify, like, what's the voltage across this resistor, then it would be the voltage at from the voltage difference from B to C, or from C to B. We just say voltage at C, I need to specify the other thing. That other point is ground. And I can put that reference point at any place I like. I could stick it over, use something I can erase. I could stick it over here if I so desired. Measure voltage from C to that. I could stick it here if I wanted to. Measure the voltage difference from C to that. And put it wherever I want to put it. I'm going to choose to put it right here. That's going to be, this is going to be my reference point for voltage. And for that means that this is my 0 volt point. So I'm measuring everything relative to that. I'm putting it there because conveniently, if I put it there, I'm measuring what's called the voltage at B is across this 12 volt source. So if I do like a summation of voltages between 0 volts and B, well, it's just that source. So it's really, really straightforward and kind of gives me one answer, just kind of, it gives me one of my node voltages just kind of sitting here. So I'm going to choose to put my ground right there. However, yeah, let's get this show on the road. We need to find the voltage from C to ground. Great. All right. So what do we got? For doing the node voltage method, It means that we're trying to express the currents going into each node as a function of voltage, right? So a couple of things that I can tell that one is that the node voltage at B would be what? Negative 12 volts. I can say that because if you look at a voltage source, the labeling of a voltage source, this voltage source is specified, I guess that's a better way to say it. This source is specified as being a 12 volt source, a positive 12 volt source. That specification always applies to the voltage that's applied by this end, the positive end of the source, the plus end of the source, relative to the negative end. So if I measured across this source, it'd be 12 volts from this end to that end. If this was a negative 12, it'd be negative 12 volts from this end to this end. The specification's always for the positive end relative to the negative end of the source. So VB is then, if I go from 0 to B, I'm starting at 12 volts, I'm going down to 0. So 12, so it's a 12 volt drop going towards B. Or if I ask what's the voltage at B relative to 0, it's 12 volts below 0. So you dropped 12 volts going from 0 to B. Okay? So VB, I know straight off the bat, that node voltage is negative 12 volts. Ba-bam. What else do I know? Along that same lines, if I go from A to C, I go across a 10 volt drop, right? So go from A, I start at 10 volts, I go to 0, I'm at C. So VA to VC, or VA minus VC, the difference in potential between those points is 10 volts. Now you might think, okay, wait a second here. There are a whole bunch of different ways to get from A to C. I can go up here, I can go across here, I can go through here, I can go like that. How is it always 10 volts? Well, remember when we talked about parallel circuits? If I have multiple parallel branches from they're all going to start at the same voltage. There's going to be, and if they meet up in the same place, they're all going to have, there's always going to be the same voltage drop across each branch. It might be distributed differently across each branch, but say you have a circuit, some load source. Got 2 resistors here, 1 resistor here, other resistor here. This source is pushing with some amount of pressure, if you will, that forces electricity around here. No matter how many times I split up that current, it'll still have the same pressure behind it. Remember, current is the flow rate. It's the volume of electricity, if you will, that's going through the wire. And that's going to split, right? If I have a hose and it starts with a liter of water in it, and I'm pushing that liter of water along, I only have a liter of water. I can only split it up so many ways. But I can push as many splits in that with the same pressure as I want to. And that's what this source does. It's pushing with, say, 10 volts on each of these, on the flow in each of these wires. The flow itself in each wire, the current itself in each wire might be different, but the pressure pushing it, the voltage pushing it is the same. In the same way, if I have such and such a voltage from A to C, doesn't matter what way I use to get to C, it's going to be the same pressure pushing you towards C in each direction. So VA to VC, always 10 volts. Bam. Okay, so know that straight up. Okay, so I got a couple of knowns. I think that's all the things I can intuit straight off of the circuit diagrams. Now I have to start drawing equations. So let's see what we got. if I look at this node here, let's do a Kirchhoff's current law there. So I probably should draw some directions. So I'm going to say I have some current going in there, call that I 10 volt. I got I 10 ohm there. That's going to go out. I'm going to arbitrarily pick that direction. I'm going to say that there's current going that way. This is going to be I 40 ohm. Great. And these current sources kind of pick the direction of current for me. Current's going up in this wire, current's going down in this wire. Remember, everything on this wire, like right from here to here, is in series, right? Everything in series has to have the same current. So everything on this wire is 2 amps, and it's going in the direction of that arrow. Everything on this wire, the current in this wire is 5 amps, and it's going in the direction of that arrow. So I'm not going to bother writing those in. Okay, so for A, I probably should write in the arrow here too. I12 volt. There we go. All right, so those are all my currents. So if I do Kirchhoff's current law at A, gives me, let's see, 5 volts, 5 amps in plus I 10V equals I 10. Great. So I'm seeing the chance that I might be able to simplify things here because A and C are both going to have I 10V in them. So let's do KCL at C as well. Let's see what's going in and out. Here, everything's going out. That might seem to violate some like conservation of charge thing, but don't worry, we've just chosen direction so that we have a sign convention to follow. If something's not going the right direction, it'll come out in the math. So we're okay. So I have, let's see, I 10V going out. I got 2 amps going out. Got I 40 ohm coming out. Great. That equals 0. All right, so I got an I 10V in each equation. So let's just solve for those. Solve for I 10V and set those equations equal to one another. So oops, sorry. There we go. That should be a minus. Sorry. This is why I shouldn't skip steps. So negative 5 amps plus I 10 ohms equals I 10V equals negative 2 amps minus I 40 ohms. Cool. All right, so this isn't that helpful in the grand scheme of things. I guess I can simplify this and get negative 3 amps equals negative I 40 ohms minus I 10 ohms. Cancel out negative and get that. But I need to put these currents in terms of node voltages if I'm ever going to get something out of this. So let's do that. So I know from Ohm's law, the voltage across a resistor, remember the voltage across a resistor is equal to the current through that resistor times its resistance. So the voltage across, say, this 10 ohm resistor in terms of the node voltages would be like VB minus VA or VA minus VB. The difference between those two would be the voltage across it. In this case, we have current drawn going from left to right. So that means that you must have more potential energy at A, more voltage at A than at B in order to move from left to right, because it goes from a place of more energy to less energy, right? It's kind of like if I drop a brick, it goes from a place of high gravitational potential energy to low potential, gravitational potential energy. So current travels from high energy to low energy. So in this case, the voltage across the voltage across the 10 ohm resistor would be VA minus VB. And then to get a current, I divide by resistance. I'll do the same thing for this resistor here. So I have the current drawn going this way. So to be consistent with that, the voltage must be higher at C than at B. So VC minus VB over 40 ohms. There we go. And I know that VB is negative 12, so that gives me one thing right off the bat. And I can make a substitution for VA or VC from here. So I'm probably going to be able to solve for something really, really soon. So let's do that. Also make sure that I didn't make any sign errors while I'm sitting here. Checking back on something that I did before, make sure I didn't screw anything up. Okay, I think I've taken care of any sign problems. We're going out from there, 2 in, 1 out. Yeah, I think we're okay. Okay. This 2 in, 1 out, 3 out, no in. Great. So pull it down. Solve this for item B. Those will have opposite signs always. This guy, item B is that minus that. Great. Okay, great. I think we're okay. I think that we're okay. Cool. All right. So let's do some substitutions here. So VB is negative 12, and then the VA is 10 volts plus VC. So yeah. Paper here. Write that out again so we have it. All right, let's do some division, combine some like terms. Let's see, 1 over 40 is, I believe, 0.025. Let's double check. So I'm going to drop some units. I'm going to drop the unit notations here because it's going to get very confusing soon. 12 over 40, pretty sure is 0.3. That combines to be 22. Okay, so that's 3 equals 5 VC plus 2.5. So that's 0.5 equals 0.125 VC, or it's just 1/2, 1/8 VC. VC equals 4 volts. And that's the show. That's how we use node voltages. Put this in the right order. There we go. So you saw how we started off by defining a reference location, a place where we want to attach ground. We tried to put it in a spot that would be convenient for us in terms of finding out one of the node voltages. We shall note that ground is at a node here. So the voltage at, if I labeled this node D, VD would be 0 because at ground. Other notes. We did not write a node equation for B. If we did, we would have had to include I12 volts. We cannot just use Ohm's law and say that there's some like resistance for that voltage source because it's not a resistor. It's a source. So we have to just have I12V in one of these equations. If you wanted to write it out, it might look something like this. So so if I was to write out Kirchhoff's current law for B. Let's see, I have 2 going in, 1 coming out. So and I have all my node voltages now. Well, I have C and I have B. Don't have A yet, but if VC is 4, then VA is 14 volts. Just now a little bit, see everything. So that means that let's see, A minus VB over 10 ohms plus VC minus VB over 40 ohms equals, let's see, 14 volts minus negative 12 volts over 10 ohms plus 4 minus negative 12 volts, 40 ohms. That gives me 26 over 10, right? Yep, 26 over 10, so that's 260 plus 16 over 40. Oh, over 10, whoops, 2.6, not 60, so 2.6 amps plus 0.4 amps. I12V is 3 amps. So I can just do another node equation and get that guy. All right, I think that's that. Let's see if he can pull off a mesh equation now. All right, so this is from a little bit later on in the book. Get the right one. Yeah, that looks like it. This is from page 134, example 4.6-1. So circuit in here. Note that I'm still drawing nodes in, even though we're doing mesh currents now. Okay, let's see. This guy's 1 ohm. This guy is 1 ohm. This guy is 2 ohm. All right. We'll just throw some things on this. I think we tried this during class, so let's get it on. So, all right. So we could go after this using the node method. It's going to end up going to be easier using the mesh current method instead. And if you want to try each of these problems using the other method, I think you'll see why it's easiest to do them with the method that we chose. I think it just has to do with what information you have readily available. So let's give this a shot. So mesh currents. There's one mesh. Find the current going clockwise, I1. Same here with I2, here with I3. Okay, so first thing I can see, again, like with the node method, we want to see what we can do to make this as straightforward as possible from the outset and get as many known things as we can just from the outset. So this current source in the center, you might think we could use that to define a current, but well, I have mesh current here and a mesh current here. Those mesh currents, remember, these aren't physical currents. They can combine to be a physical current, but these mesh currents are not necessarily physical. They're computational constructs to help us analyze this circuit. This would be different than, say, these node voltages. If I stuck a voltmeter probe here and here, I would get that node voltage. Mesh currents are a little bit different. They're not necessarily something that I can stick a probe in and measure. So like this 5 amp source, this wire must have 5 amps running through it, right? We said that before. This whole thing's one wire. It's in series with itself, if you will. It's in series with the current source. It's got to have 5 amps through it, period, no matter what the mesh currents are. So we do know that we have mesh current I1. It's going, based on the direction that we have it going in, it's going down in the same direction as the 5 amp arrow. The difference between I1 and I2 must be 5 amps. Because I2 is going in the other direction, and those two have to combine in order to make what's actually in this wire. Now, if we look at up here at I3, well, it's the only mesh current that touches this current source. Therefore, we can just say straight up, I3 is 4 amps. And I3 is going in the same direction as 4 amps. That's why it's a positive number. So I3 is 4 amps. It's the only mesh current that touches that current source, and it's going in the same direction as the current source. Awesome. Great. Okay, so I think that's all the information we can glean from the outset. So let's see what we can do here. So I'm going to start off. Start off in here. So I know that I have these loops, I have these mesh currents, and I want to try to do Kirchhoff's voltage law along each mesh. Excuse me. I'm going to do Kirchhoff's voltage law along each mesh in terms of these mesh currents. So for mesh 1, I'm going to start here, go up. So I'm going from the negative terminal of the voltage source to the positive terminal. So I'm going from 0 to 10. That's a negative voltage drop. Great. So I get negative 10 volts. Up here, go around. My mesh current is going across this resistor. So I'll see a voltage drop of 1 ohm times I1. Then I come to this 5 amp source, right? Well, it's pushing current, right? It's pushing a specific amount of current, it's a current source. But if you're pushing current, you're using voltage to do that. You have to. So I'm going to so I'm just going to designate a positive side and a negative side of it. It's pretty arbitrary. No matter what direction I choose now, the actual direction will come out in the math. So I'm going to say the positive side of the higher voltage side of that current source is here. And it has a voltage of V5A. And it goes down. So the voltage goes from whatever it is on this side down by V5A volts by the time it gets to here. Okay. So say that there's a voltage drop of V5A. So I come around this loop and go across that source. I'm back at the beginning. So that's 0. Awesome. All right. So let's do that for mesh 2. Obviously, I need at least a couple things to figure out my unknowns here, right? Oh yeah, I probably should say I want to figure out what my mesh currents are. And then I want to figure out the voltage between C and A. All right. So mesh 2. So say I start here, going in the direction of my mesh current. So I'm going to have a voltage drop, 2 ohms times I2. Over here, okay, I'm going from this lower voltage to some higher voltage. So I have a negative voltage drop of a magnitude V5A. Right? I'm going from a lower voltage to a higher voltage because that's what I've designated here. Come around here, going in the direction of my mesh current. So voltage is going to drop across this. What is this called? This resistor. Whoopsie. Before I get too far, I need to correct myself here. My apologies. We'll do it right for mesh 2, and then we'll go back and fix it in mesh 1. So to go across this resistor, and if any of your internal alarms went off when I messed this up for mesh 1, good for you. I'm going to go across this resistor. Yes, voltage is dropping by 1 ohm times whatever the current is. The current's a combination of not just one mesh current, but 2 mesh currents. And this would be the same for mesh 1. I screwed it up there. So you have mesh current I2 going this way, mesh current I3 going the other way. So the difference between those is the voltage drop across here. So I'm going to write that as I2 minus I3. I'm writing it as I2 minus I3 because in the direction that I'm going, if I2 is bigger than I3, I get a voltage drop going in the direction of the mesh from left to right. If I3 is bigger than I2, it would be a negative voltage drop going left to right in the direction of the mesh. So that's why I'm writing it like that. Go back and fix it here. Again, I'm going from left to right, so it'd be I1 minus I3, not just I1. All right, great. So, see, I know what I3 is. I don't know what I2 is. Don't know what I1 is. So I have 3 unknowns here, but this is similar in both of them, right? And I also have this equation up here. I think I can get rid of another unknown. I can get rid of I1 or I2 down here. So I'm going to set both of these equal via V5A. And I'm going to make a substitution for I1 or I2 so I can solve for the other one directly. So let's do it. So for mesh 1, V5A equals 10 volts minus 1 ohm times I1 minus 4 amps. Make that substitution for I3. And for mesh 2, V5A equals 2 ohms times I2 plus 1 ohm times I2 minus 4 amps. Make a substitution for I3 there as well. They set them equal to one another. I'm also going to start dropping my unit notation. It's going to get very confusing in a second here. Let's combine some like terms. So we got a 14 plus 4, it's an 18. All right, I1 is 5 plus I2 if I solve this guy out. So 18 minus 5 minus I2 equals 3 I2. So 13 equals 4 I2. I2 equals 13 over 4, or what, 3 1/4. Okay. I2 means that I1 is just 5 plus that. That's 8¼ amps. Awesome. That's 8.25, I promise. All right, great. Got that, got that. You saw how straightforward that was. Like, we found the currents very, very, very directly, kind of like we found voltage very, very directly here. That's what the two methods are. That's what each method's good at. Let's figure out how to get the VCA though. So I know that the current in this wire is I1 minus I3. That's what we said when we figured out the voltage drop across that resistor. 1 ohm times the current through that resistor. So current through the 1 ohm resistor, I1 ohm, 2 ohm, is I1 minus I3. The difference of those two mesh currents, that gives me 4.25 amps going through that resistor. Voltage across that resistor, or the voltage from C to A, would just be that current times resistance of 1 ohm. It's 4.25 volts across that. And I know that it's higher here than here because, again, I said if I1 is greater than I3, voltage drop would be in the direction of the mesh current. Well, I1 is 8.25. Subtract 4 off of that means the actual current's going in that direction, consistent with what my sign convention was when I made these mesh equations. So I know that this is the voltage drop from C to A. It's higher at C than it is at A. All right, so that's mesh equations. It's node equations. Talk about them a little bit more, but if you have any questions, feel free to reference this and feel free to ask.